Great. So I'm going to talk a little bit about, this is a paper that I just shared at the NIME a few weeks ago. It's on designing percussive timbre remappings, negotiating audio representations in evolving parameter spaces. And I conducted this work with Rodrigo Constanzo, Harlan Posaitis, Andrew Robertson, and Andrew McPherson. And so the core idea of this work is to enable percussionists and producers to directly control synthesizers in real time from drums. And so my goals for this work is to support live performance, so to enable more expressive controls of synthesizers from acoustic instruments, as well as to support sound designers to enable more dynamic synth modulations and to be able to extract those directly from audio and inspire new ways of working with audio synthesizers. And so I'll just give like a little background and overview of what this looks like. And so we start off with a drum performance. So this is a short drum performance on a snare drum. And so in that phrase, you'll see that on this side, I've plotted each note in the phrase in an audio feature space. And so the X on there is the first note in the phrase, and each subsequent hit is plotted around that. And I have this arrow showing the vector difference between that first note, which I use as an anchor, and show the vector difference between each subsequent note. And so this vector difference is important for the next stage of the timbre remapping. And so here we introduce a synthesizer, and there's a preset for this synthesizer, and we plot this preset in that same audio feature space. And the goal of the process is to find a set of modulations so that we have the exact same set of vector differences transposed onto the synthesizer. So in the same way that we might transpose a melody from one key onto another by looking at the relative differences in pitch, the idea here is to take the relative differences in audio features and transpose that onto the synthesizer. And so I'll show what this sounds like now. So I'll play the same phrase, and then it being mapped onto an 808 synthesizer. So it's a touch quiet, but you can hear that you're getting some of the dynamics being modulated, as well as some of the more subtle timbral differences being mapped there. And so that's an overview of what this is, and I'll talk a little bit about how we did this. But first, so what are some of the problems that we encountered in this work? The first is this idea of audio representations, and how do we represent this problem? So there's some set of features that we probably want to map directly onto the synthesizer, such as rhythm. We probably want the rhythm to follow directly, as well as loudness. But then there's this more nebulous concept of performance variations, is how do we map the timbre variations in this performance? And one of the main issues here is that these audio representations don't necessarily map to perception in a clean way. And so designing these has a really big implication on the end result. And in design theory, they talk about this as a wicked problem. It's an ill-defined problem. And so figuring this out is one of the things we were looking at. Assuming that we can find some suitable representation, then we have this problem of, well, how do we actually find synthesizer parameters that match the audio features that we want? This is this non-trivial inverse problem of moving from the audio space to the synthesizer parameter space. And then finally, we want to put this together into a real-time system. We ultimately want something we can play. And so we need to do this in latency that's less than 10 milliseconds, so they're below that perceptual threshold. And so to deal with some of these, like the wicked problems, so to speak, we turn to this process of iterating between technical practice and musical practice. And importantly, the second author of the paper, Rodrigo Constanzo, is a professional percussionist, but who also works a lot with machine learning and machine listening. And so we situated this research within his practice to be able to try to understand it more in a musically contextual way. And so by technical practice, I mean doing audio analysis, doing statistical analysis on audio features, writing max patches, coding, training models, and then feeding this into musical practice, where we're performing critical listening, reflecting on that, as well as performing with those systems and doing this in this iterative process. And so even though this was an iterative process, I'll talk a little bit about the technical system we developed and then share a bit more about the practice-based approach. So it's a two-stage process. The first stage is the parameter search. And so we have our synthesizer with a preset, and then we have a short recording from a drum, and this defines the set of variation we expect while playing. And so we then extract each of the notes in this phrase, We're looking at short windows of audio, but it's about a quarter of a second, so we can see how the drum sound evolves over time. And we do the same feature difference extraction process that I shared at the beginning. And then this feeds into some synthesizer parameter search, where we iteratively look for synthesizer presets. And in this work, we use a genetic algorithm. I won't go into the technical details of this in this short talk, but the idea here is to iteratively optimize synth parameters to match audio features. The nice thing about this is that it works with black box synthesizers, including hardware synths, and we did apply this to modular synths like Euro racks, as well as audio plugins. And one of the things that we introduced in the paper is an ability to optimize many modulation targets at once. So typically with a genetic algorithm, you have a single search target and you're searching for the best solution for that target. But here we're looking for many variations at once. And so we came up with a method to have many, maybe hundreds of targets at the same time. And then we used a clustering approach to be able to select the best items for the next iteration. I'm happy to talk about that a little bit afterwards if people are interested. But the next stage is this real-time mapping system. And so out of the genetic algorithm, we get a data set of drum features as well as matching synthesizer parameters that match our input data set from the drum recording. And then this is passed into a real-time system. And so to do this real-time mapping, we have our drum input and an onset detector. And so this detects when there's been a new hit on the drum. And then what we do is we extract a very short segment of audio. We extract 256 samples following a detected onset, which is a little over 5 milliseconds of audio. This is passed into a feature extraction algorithm. And so what we get here is a set of onset features just at the very onset. And so what we want to do is we have our data set of synth parameters that we found from the genetic algorithm. But the issue is that these were computed on longer windows of audio, about a quarter of a second. So we have this mismatch between these two feature sets. And so what we do to deal with this is we introduce this idea of a timescale regressor. And so we train neural networks on a single drum and to be able to predict from these short segments of audio, about 5 milliseconds, how that sound is going to change on the drum over the course of the next quarter second. And so then we can do this in real time, get the features, and then use those features to query this data set of synth parameters so we can perform in real time. And so one of the things we spent quite a bit of time looking at in this work is the effective audio representations. And so we selected a set of audio representations based on some of Rodrigo's previous work, as well as what's available in the Flacoma package in MaxMSP. And so this includes a hybrid descriptor set, which includes loudness as well as some timbral features and pitch. Mel bands, so a set of subbands across the spectrum, some timbral features, so some different statistics applied to spectrums, as well as Mel frequency Kestrel coefficients, and a large number of statistics applied over this. So this becomes quite a high dimensional feature. And so each of these have different characteristics that they represent about the audio. One of the nice qualities of these last two is that they're less sensitive to loudness variations or loudness invariant. And so this is potentially a nice quality for this timbre remapping problem. And so we applied both some technical based feature selection processes that I talk about more in the paper, as well as practice-based experiments for this. And so for these practice-based experiments, we had a set of recordings that Rodrigo recorded that we could listen to, as well as we just spent time performing with them and listening and journaling and taking notes. And so we fed these through each of these different descriptors, and we had a set of different synthesizers that we experimented with, including an 808 drum synth, Quantassi, which is sort of like a chaotic oscillator, a physical modeling synth called Derailleur, a hardware Eurorack synth, as well as an FM drum synth. And so one of the things that we were looking at in this is, well, how do we define what a successful mapping is? And this is actually kind of a hard problem. And in a way, it was sort of like, we were like, well, how does it feel musical? And this is a bit of like a nebulous concept to unpack. And so from analyzing our journals and conversations through this process, we were able to come up with some like 4 more concrete criteria for success in the timbre mapping. The first is this notion of consistency. This had to do with the variation of the mapping, where we had mappings that were too noisy or had too much variance, which weren't really playable. And similarly, if they didn't have enough variation, then they were boring. Then there's this notion of repeatability. So could we repeat gestures with intention and get the same result back, allowing us to actually build out larger musical ideas? Then there's perceptual alignment. So this was sort of like the direction of the timbre changes. Did they match the perception? So for example, like hitting on the membrane of a drum and then hitting on the rim, you get this increase in brightness. And was that reflected in the synthesized output? And we were sensitive to this. Okay, go quicker, Horace says. Um, and um, and then finally, this notion of plausibility. And so were the synth parameters, were we able to solve these in plausible ways? And this was most noticeable with frequency parameters. So for example, sometimes frequency parameters were used in very non-drum-like ways to solve something like spectral centroid. And this was deemed not so good. And so then we spent quite a bit of time actually just playing with these and patching. And so I'm just going to play a couple examples of some end results of this. Great. And then the next patch, and I'll talk just a little bit about this, is one thing that wasn't handled particularly well by the system was morphology, so how the synthesized sounds changed over time. We found that we were able to get really nice subtle variations, but dealing with the morphology was a bit trickier. And so we came up with a patch to deal with this. And so we have our original system here, which has a single time scale regressor, which maps from the onset features to the full features. But we introduced two other sets. So we actually computed features over different time scales. So one over 100 milliseconds, one over just the onset. And then this created three different data sets of synth presets that we could then select from. And then we were able to interpolate over these over time and pass these into the synth. And so we had these then evolving synth presets, which allowed us to affect morphology a bit differently, as well as just introducing an amplitude envelope for control. And yeah, example of this. Great. Okay, so just to wrap up, in conclusion, timbre remapping is a challenging problem. Defining and representing timbre is an ill-defined problem. To deal with this, we turn to this process of technical practice, iterating with musical practice, and really centering Rodrigo's musical practice in this and listening and performing. Synthesizer parameters are complex. To deal with this, we look at this genetic algorithm approach to navigate them. And then the challenge of creating a real-time system. And to do this, we introduced this notion of a timescale regressor to enable real-time performance. And just a quick shout out to Physical Audio. They gave us some VSTs to perform with, which was really nice. And yeah, that's the presentation.